Guys, we'll wait for some time and then again we'll start the class, okay? Just wait for 5 to 10 minutes. Meanwhile, you can take some beverage or something, whatever you like. You guys are here, right? You just joined the call and left, and I'm the person who was speaking here.
Oh, sir, we are here, sir.
Okay, cool. So just take 5 to 10 minutes of break, okay? So shall we start? Guys?
Yes, sir.
Okay. So we'll start, okay? So how far we are done? Any idea? Narayani?
Current and electricity we started, sir.
We started current electricity. Okay. Obviously, we started current electricity. I had given you a lot of definitions and some concepts we have studied. Yeah, right. So we have covered till, I think, have we discussed specific resistance? No?
So I guess we have completed till series connection, sir.
What structure?
Series connection.
Okay, series connection, yes. Tell me the definition of electric potential, anyone? What is electric potential? You have done in school quite a lot of times. So tell me what's the definition? How you will define this electric potential?
The potential difference?
No, it's not the potential difference. Anyone? Atish? How about you? Can you define electric potential? See, okay. We did on Monday, I said. Monday or Tuesday, right? This Monday or Tuesday. And for you, Narayani, we have done it in previous class. Okay. Anyway, so what we'll do? See, suppose let's fix a reference frame. Okay, let's say this is our reference frame or the coordinate system that we call. That's wrong. Okay. Okay, so this is our coordinate system. So let's say this is X and Y. All right. Any doubt? Anyone? Just stop me there itself and we can discuss it. Okay. So let's say this is our coordinate system and there is a test charge. Okay. Some test charge is here. Positive test charge. Positive test charge. Okay. Let's say this is at infinity. This distance is infinity. Of course, it doesn't make any sense, right? Now, how it is defined, we are just trying to understand that. Now, suppose you are bringing this test charge from infinity to some point near this coordinate system with uniform velocity. Okay, now let's say this positive test charge is here. Okay. And here the acceleration is 0. And this is uniform velocity. Okay, so if you bring a positive test charge from infinity to some point, okay, with constant velocity, okay, or speed also you can write because we are talking about magnitude. Okay, so see, what's the difference between speed and velocity? This is your velocity, okay, which you can represent by Vx I cap plus V. Okay, you haven't studied vectors, right? I'm sorry. So this is your velocity vector representation and its magnitude. That means if you take the modulus, this is called speed. Okay, you'll study this, don't worry. So you can write uniform speed or velocity, both are fine. If you bring a positive test charge from infinity to some point, okay, the work done, the work done per unit charge is called electric potential. So electric potential is represented by V, which is equal, which is equal. See, now it is writing. Okay, so V is equal to work done upon this charge. Let's say this charge is Q, positive charge. So this is Q. We represent charge by Q, right? How do you define electric current? Anyone? It's been some time, so let's have a definition of that as well. So this is called your electric potential. Okay, so you will define it as, now just if you can understand this diagram, it's really easy to define it, right? You are bringing a positive test charge from infinity to some point, which some point means which we can locate, okay, with uniform velocity or speed is called your electric potential. the work done per unit charge. So this is called electric potential. Now, what's the unit of electric potential? From here, what you can say? This. What's the unit of electric potential? Anyone? Dude, you can just see here, right? What's the SI unit of work? It is joule, right? And what's the SI unit of charge? Coulomb. So joule per coulomb is called your electric potential, which is also called volt. Volt is equal to joule. Why this is not writing? Joule per coulomb. Okay. So this is also called volt and represented by V. So whenever you are writing V in your paper, or whenever you are studying about electric potential difference as V, that is actually you are writing V2. So what is the definition of electric potential? Sorry, potential difference. How you will define potential difference? See, now let's assume there is another positive test charge at infinity again. Okay. And again, you are bringing it to some other point. Let's say here. With same acceleration is equal to 0. Now, this was the first. This is the second test charge. Okay. So its potential is V1. Its potential is V2. Okay. So potential difference is V2 minus V1. That's it. Is your potential difference. That means you are moving a positive test charge from this point, from this point to this point. The meaning is that. Okay, so this is called your potential difference. Okay, and V2 minus V1, which you usually in the book when doing calculation, you write as V. But this is not correct, by the way. Okay, you have to understand this. It's always V2 minus V1. Okay. Yes. And what will be the unit of electric potential? Sorry, potential difference is the same, volt, which is joule per coulomb. Okay. So you can write J upon C, which is equal to volt V. Okay. So this is the SI unit of electric potential or potential difference. All right. Anyone there? Okay, 9 participants are there. Neeraj, is that clear? The masked man. Huh? Still you are wearing mask? Are you wearing mask right now? Huh, Neeraj? No? Okay. So you guys are in home. That's what I understand. Tanishka is traveling, I suppose.
No, sir, not today. From tomorrow.
Oh, what was that? Who was that? That with loud music? Jyoti, was it the discipline committee or Afan?
No, sir, it was not me.
Okay. Afan, what, Adidas or Reebok?
Sir?
Nothing, just pay attention here. All right. So you understood what's the difference between electric potential and potential difference? Fine. You have had this definition before, right?
Yes, sir.
Yeah.
Sir.
So how you will define electric current? Let's go in. It seems like you guys have forgotten a lot of things. You have forgot a lot of things. How you will define electric current? I is equal to, Narayani?
dq by dt.
What is dq by dt? Tanishka?
I, sir.
What is this dq by dt? What do you mean dq by dt?
Change in time
Yes.
is dt.
Hmm.
And dq is charge, sir.
Yeah. So it's called rate of change of charge. Okay. So when there is flow of charges, or that's written in your book, of course. So the rate of flow of charges is called electric current. Okay, so that means what's the SI unit of current?
Ampere.
Ampere. Okay, so from what's the SI unit of this charge?
Coulomb by second.
Coulomb per second is your ampere, right? That's what we are calling ampere. So what is 1 ampere of current? Is the amount 1 coulomb of charge passing through the cross section of the conductor, in 1 second is called 1 ampere of current. Okay. Yes or no? Any doubt?
Yes, sir.
No, sir, no doubt.
Yes, sir.
If you have doubt, let me know. Okay, just turn on your mic and stop me there. Okay. How many of you remember Coulomb's law? Why we are saying a lot of times Coulomb. But why Coulomb? Why the charges are as a unit of charge is Coulomb? Huh? What is Coulomb's law? Huh? Coulomb's law. See, Coulomb. He
Sir,
gave
I didn't understand your question.
See, we have been talking about Coulomb a lot, right? Joule per Coulomb. As a unit of Coulomb, the charges are Coulomb. So I'm asking why Coulomb? What law Coulomb gave that made him famous? Kind of that. He was a Frenchman, right? French mathematician or French physicist. Anyway, so he gave the relation between the force, electrostatic force between two charges. Okay, so suppose the charges is Q1 and this charge is Q2. Okay, it can be positive, it can be negative, doesn't matter. If both are positive, if both are same charges, it will repel. If both one is different charge, then it will attract. Unlike gravitational force, Coulomb this electrostatic force can be attractive or repulsive. But gravitational force is always attractive in nature. Okay. Now the separation between these two, let's say, is D. Okay. So what Coulomb said that you have also Newton's in Newton's law also you have studied this thing. Okay. So F F is directly proportional to the product of charges, product of magnitude. Just give me a moment. I think there is something wrong with the tablet. Okay, let me try again. So F is directly proportional to the product of magnitude of their charges. That means whatever value of Q, even it is negative, will take positive, and force is inversely proportional to the square of distance between them. Okay, that's what Coulomb said. Okay, according to Coulomb. So if you combine these two, what we can write? F is proportional to Q1 modulus Q2 modulus upon D square. Modulus, why we are writing modulus? Because we just want positive value. We don't want negative value. Because we are calculating the magnitude only here. Okay, not the direction. All right. Okay.
Yes, sir.
Yeah. So to remove this proportionality, we need to put a constant here. Okay. So this will be equal to K times Q1, Q2 upon D square. And this K is found out to be 1 upon 4 pi epsilon naught. Okay. Where epsilon naught is called the permittivity of vacuum. Okay. It's called absolute electrical permittivity of vacuum to be precise. But you can say permittivity of vacuum. Okay. So and the value of this epsilon naught is, I think, 8.8 something into 10 to the power of minus 12. Okay. And unit, what will be the unit of this K? Anyone? What will be the SI unit of this K?
C square by Newton meter square.
Tell me.
C square by Newton meter square.
C square. What is C square?
Charge.
What is C?
Coulomb.
Okay. So see, we know the SI unit of force, that is Newton. Right? Newton. We don't know the SI unit of K, right? So let's leave K as it is. So we are writing SI unit. Okay. So K, and this is Coulomb. Q1 is Coulomb, Q2 is Coulomb. So it will be Coulomb square upon meter square. So from here we can write K, the unit. Obviously we are writing SI unit. So let me raise SI unit of K will be equal to Newton meter square upon Coulomb square. Okay. If you are finding now, we what's the unit of SI unit of epsilon naught? So we know epsilon naught. So how we can find it? How can we find this? We know a relation between epsilon naught and K, right? So we know K is equal to 1 upon 4 pi epsilon naught. Now 1 upon 4 pi is a constant, right? So it will not have any unit. Okay. So SI unit of K we already know. So epsilon naught we can write is equal to 1 upon 4 pi into K. And since if we are writing the unit, so SI unit will be, now epsilon naught SI unit will be equal to, now 1 upon 4 pi, it doesn't have any unit, but 1 upon K we have. So 1 upon K, the unit is Newton meter square per Coulomb square. So this will be Coulomb square upon Newton per meter square. Okay, so that is the SI unit of epsilon naught. And epsilon naught is called absolute electrical permittivity. So you can just write absolute permittivity, or let's write it. Electrical permittivity of vacuum. Okay, so this is called absolute electrical permittivity of vacuum. So from like we have studied mu naught, right? Or N naught, I think it was there, N naught, the refractive index in a vacuum, right? N naught is equal to 1. That's what we have studied. So it's kind of similar to that, but not exactly. This is not equal to 1. So epsilon naught, the value of epsilon naught is approximately equal to 8.85, I think, into 10 to the power of minus 12. Unit is Coulomb square per meter, per Newton per meter square. Okay. So this law, so we can write electrostatic force is equal to 1 upon 4 pi epsilon naught 4 pi epsilon 4 pi epsilon naught into Q1 Q2 upon D square. So this is Coulomb's law. Okay. So this is what Coulomb's law is. All right. Yeah.
Yes, sir.
So tell me how many charges are there in one electron? What is the amount of charges in one electron? Atish, can you answer this? Atish, can you hear me? No? Okay. Okay, so we'll move ahead. And we have also studied Ohm's law, right? Ohm's law we are done with. Right? So,
hello.
Yeah. Hi. Who's this?
Can you hear me, sir? Atish.
Yeah, Atish. Tell me. Ohm's law. What is Ohm's law, Atish?
Sir, V is directly proportional to I. When it is plotted in a graph, there would be a straight line.
Okay. Good.
V To bring it as a formula, we introduce a constant called R, which is resistance, which is V is equal to IR.
Okay, correct. So what is resistance? It's fine if you don't know, it's completely fine. So if suppose, what does the slope represent? Huh? Anyone? What does the slope represent? What is slope? Theta, right? Let's say theta 1, theta 2.
Tan theta, sir.
Yeah. Tan theta is the slope. Of course, it is the slope. But for this graph, what is tan theta? Okay, you are saying tan theta. Let's write tan theta. What is tan theta? Tan theta is V upon I. Right? Actually, delta V upon delta I. We have discussed this. Change.
Yes, sir.
Right? Okay. When delta I tends to 0, we write it dV upon dt, but that's not the point here. So this, we know V is equal to IR, right? Remember, that's just now Atish said, this is Ohm's law, right? That means if you substitute it here, you will find this is equal to R, the resistance. That means the slope will give you the resistance in VI curve, okay? The slope will give you resistance. Understood or not? Yes? Let's say this is first curve and this is second curve. That means R1 and R2. So tell me, which resistance is more, R1 or R2? Jyoti, which one is more, R1 or R2? Which resistance is more? Jyoti? Afan, you there? Sanjay, you there?
Yes, sir, I'm here only.
Yeah, so which resistance is more, R1 or R2?
R2, sir.
R2, why is that? You are saying R2 is greater than R1. Yeah, there. So you have 50% chance, right? Either A or B will be the answer. So why not take a shot? Fun. That's what you're doing?
No, sir.
Okay, see, which slope is more? Which slope, which theta is more? Theta 1 or theta 2? Theta 1 is greater than theta 2. That means tan theta 1 is greater than tan theta 2. Okay, that means tan theta is R, which is R1 greater than R2. Simple. Okay, understood? And this is VI curve. Got it, everyone? Okay, I am not getting. Okay. See, also we know the resistance is directly proportional to temperature. Okay, so if you increase the temperature of the conductor, the resistance of the conductor will also increase. Okay, so that means if I draw a VI curve, I have done this in class, right? I have done this, I remember. So again, if this is 1, this is 2, VI curve. So if suppose this is T1, this is T2. So which resistance is more? Of course, this R1, R2, right? So we know R1 is greater than R2 here. That means T1 is greater than T2. Okay. So with increase in temperature, the resistance will also increase. Okay. Yes or no? All right. Let's do a problem. Narayani. Tanishka.
Yes, sir.
Yeah. Answer this. Yeah. What does the slope represent?
1 by R.
Tanishka, what does the slope represent?
1 by R, sir.
1 by R, right? Why? Because see, this is IV curve. Okay. We know V is equal to IR. And when we are writing slope, we write change in y upon change in x. Now in x, in y, what we have? In y, we have I. So that means delta I upon delta v we are writing. Now from here, if you write I upon v, you'll get 1 upon r, right? So that's why we are getting here 1 upon r. Okay, got it? So it is called conductance, okay, and represented by C only. The opposite, the inverse of resistance is called conductance. So this, let's say this is conductance 1, this is conductance 2. So of course, conductance 1 is greater than conductance 2, but resistance 1 is lesser than resistance 2. Okay, this is 1, this is 2. Anyone, any doubt? You can say, oh, theta here, theta 1, this is again theta 2. Now here also theta 1 is greater than theta 2. Then how come we have discussed if theta 1 is greater than theta 2, so R1 should be greater than R2. But why here it is, it's like if theta 1 is greater than theta 2, but R1 is lesser than R2. Because see, if theta 1 is greater than theta 2, that means 1 by R1, because this slope represents R1. 1 upon R1 will be greater than 1 upon R2. So from here you can write this. Okay. C is conductance. Okay. Is the opposite of resistance, 1 upon R. C is equal to 1 upon R. Okay. So that's what it is. Got it? Yes or no? Anyone?
Yes, sir.
Okay. Thank you so much for saying something, because, you know, taking classes online is like, you know, I'm talking to myself only. So it's kind of a little bit funny, but it's fine. So in series connection, anything we have left, like resistivity we have left. So resistivity is, you know, resistance of a conductor is directly proportional to the length. Resistance of a conductor is inversely proportional to its area of cross section. What does it mean? Okay, let's discuss that also. Okay, so this is resistivity. It's opposite of conductivity. Okay, and resistivity is represented by rho. In your book, at least I think it's been represented by rho. It's pronounced as rho, R-H-O, Greek letter. Okay. So what do I mean when I write L? So suppose this is a cylindrical wire. Wires are usually cylindrical, right? Isn't it? Now, if you cut the wire from here, okay, at this position, if you cut the wire, what cross section you will see? You will see a circle, right? So this area we are talking about. This is the area of that circle, and this is the length of the conductor. That means if you have thick wires, it will have less resistance. Okay, that is good for your electricity. And if the wire is longer, resistance will be more. Okay, so that's why from your from power plant to our home, when electricity comes, the wire are really long, right? So it will have a lot of resistance in them. Okay, so this is area of cross section. Let me write cross section. Okay, area of cross section it is called. So again, you can write these two. You can combine these two, and you can write it here as R is directly proportional to L upon A. Okay. Now to remove this proportionality, we will add a constant. Sorry, multiply it with a constant, which is called resistivity, rho. L upon. Now, what is the SI unit of rho? Resistivity. What will be the SI unit? See, for resistance, we know ohm, right?
Ohm meter.
Yeah. So ohm, yeah, ohm. This will be equal to rho because we don't know the unit, and upon meter, it will get cancelled. So rho is equal to ohm meter. So ohm meter is the. This is the symbol sigma. Okay. Yeah, sigma, capital sigma it is called. So don't confuse. It's a Greek letter. That's it. So we pronounce it as
Sir,
ohm.
isn't it omega?
Yeah, sorry, it is omega. Exactly. Why I said ohm? Who's that? Who said? Who said it is omega?
Narayani, sir. I'm Narayani.
Okay. Thank you, Narayani. This is omega. This is omega, not ohm, not this sigma. Sigma is this. Okay. Sorry, and thank you at the same time. All right. So is this thing clear? Now in series, how do we add resistance in series? Series connection and parallel connection. That's the next topic, right? Okay. So let's start here itself. Resistance in series. How do we add? Anyone? Atish, do you know how do we add?
Sir?
Yeah, how do we
Sir,
add?
the total resistance is equal to R1 plus R2.
But I have not given you R1 or R2. Okay,
We should find.
Okay, let me draw the circuit first. Okay, without circuit you cannot say it's not total resistance. It's called equivalent resistance. Okay, because why we call it? Let's understand this. Before this, I think it's better if you understand Kirchhoff's law. Okay, so what Kirchhoff's law? Anybody is aware of Kirchhoff's law, or sometime it is also pronounced as Kirchhoff's law? Anyone?
No, sir.
Narayani?
No, sir.
Tanishka?
No, sir.
Achha, let's try to understand this first. Suppose, let's say you have in your home system, your plumbing system, you have pipes, right? Suppose this is the main line from where water will be coming. Okay. And suppose this will go to your bathroom, this will go to your kitchen somewhere, right? Isn't it? So suppose if like 10 liters of water is flowing here and 5 liters of water is flowing to your kitchen. So how many liters of water will flow into your bathroom?
5.
5 liters, right? Isn't it? So in a similar manner, electric current also flows. Okay. Suppose you have this wire or resistance, you can say, and there is a junction. So this is also a junction. Okay. So let's say like this. So this is 1, 2, 3, 4. Now let's say current is coming in by 1. Okay. Now whatever, let's say this is I1. Now, and current is going out from I2. Okay. It is also going out from I4 and also from I3. Okay. Current is going in all direction, but it is only coming from I1. So here I1 will be equal to I2 plus I3 plus I4. Okay. It's like similar to your plumbing system in your home. Okay. How the water is going from one pipe. So that's what Kirchhoff said. Okay. This is called junction law of Kirchhoff. This is the first law of Kirchhoff's, which is also known as the junction law. So that means, or let's say if you have one more conductor from which wire is coming, let's say 5, I5. Okay, fifth wire. So this will be plus I5. So current is coming with this conductor, these two conductors, and going out with these two conductors. Okay.
Yes, sir.
So this means sum of incoming current. Sum of what I said, incoming, right? Incoming current will be equal to sum of outgoing current. Okay. Hopefully this is clear. That's what Kirchhoff said. Okay. So this is first law of Kirchhoff's first law. See, whenever we need second law, we'll study that time second law. I just wanted to give you this first law. Why we have done this, we will understand. Okay. Now, suppose you have a circuit. Okay. Let's say we have a bulb here, a fan, because these all have resistance, right? Another bulb, okay? And all are connected with a battery, or you can say a cell right now. As of now, we'll study about cell. So let's say the potential difference of the cell is V, okay? So actually it is V2 minus V1. Now what is V2? Let's say this point is 1 and this point is 2. Now you see the current will go from positive to negative terminal. So this is the current I. Now you'll see that same current is going in all conductors, right? So all resistance. So let's say this is R1, this is R2, and this is R3. Isn't it? Is it or not?
Yes, sir.
Tell me, is
Yes,
the current same current is going throughout, right? But see, when here the current will go, so this is I, and there is R1. So, but the voltage, it will get some consumed. So here the voltage will be V1. Here the voltage will be V2. Here the voltage will be V3, right? Because current will remain same. In series connections, current remains same. You see there is no junction, right? Here, there is no junction. In series connection, no junction, right? There is no junction now. So if there is no junction, same amount of current will be going in all three resistors. Okay. So if same amount of current is going now from Ohm's law, we know that V is equal to I into R, right? So V1 can be calculated as I into R1. V2 will be equal to I into R2. V3 will be equal to I into R3. Isn't it? Yes or no? See, whenever we are solving any problem, we are always assuming it's a ohmic conductor. We are not talking about non-ohmic conductors. Okay. Whenever we are solving problem. And this circuit can be represented by an equivalent circuit, which is the combination of all the resistance. Okay. And with that same potential difference, let's say V, and this is R equivalent, and the current going is I. Okay. So from here, using Ohm's law, what we can write? V is equal to I into R equivalent. Fine. Let's say this is equation number 1. Okay. Now, for this circuit, for this first circuit, this is the equivalent circuit. Okay. So this is the equivalent circuit. And from this circuit, what we can write? We know all current going in all the conductors are same, but potential difference will be same. So potential difference is different, but the sum of potential difference will be V is equal to V1 plus V2 plus V3. So this is the equivalent, this same potential difference is applied both, right? Here as well as here, in this circuit as well as in this circuit, right? Yeah? Okay.
Yes, sir.
Yes, sir.
Yeah, anybody is having doubts, so please let me know. Okay. Now from here, can we substitute all the values? So V1 is equal to I into R1 plus I into R2 plus I into R3, right? So let's say this is equation number 2. Now substitute 1 in 2. Okay, what we'll get? We'll get V is equal to I into R equivalent, which is equal to, now I can take I common because I is common in all. So R1 plus R2 plus R3. Okay. Anyone, any doubt?
No, sir.
No doubt, sir.
Okay, I'll assume no doubt and I'll move ahead. Okay, now can we cancel Afan? Can we cancel out these two? Yes. So R equivalent will be equal to R1 plus R2 plus R3. Okay, so if we have a series connection, we'll just add up all the resistance. So suppose if you have n number of resistance, if a connection has n number of resistance, So, sorry, how we'll write R equivalent will be equal to summation of R I, and I is from 1 to n. That's how we write. Okay, this is your sigma, by the way. Okay, is anybody having problem with this last equation that I've written? It simply means R1 plus R2 plus up to Rn. Okay, that's the meaning. Got it? Yeah.
Yes, sir.
So I have written a lot, and I want you to find. So I do some calculations. It's not like I'll keep doing it all the time. Okay, so the question is: suppose I'm giving you a circuit. Okay. So this is 0.3 ohm, and this is 3 volt. This I don't know how much, and the current is 0.1 ampere is going on, and R equivalent is given to you as let's say how much, 1 ohm. Okay, find, let's say this is R1, find R1 and voltage, means potential, not voltage, it's wrong to write like that. Or less potential difference. Potential difference in R1 and R2. Suppose this is R2. R2 is equal to 0. So this you need to find out. Do it. Then, anyone?
Sir,
Yeah, tell me. I'll give you 2 minutes, okay? I think 2 minutes is more than enough.
Sir, can I do
Yeah.
that, please?
Got it?
Yes, sir.
How much you got? R1, how much is R1?
R1 is 0.7 ohm.
0.7
Ohm.
Okay.
V1 is 0.07 volt.
Okay.
V2 is 0.03 volt.
Sure. It makes sense, right? And does it make sense? Hmm?
Yes, sir.
Yes, sir.
How you will get R equivalent? How does it make sense? You tell me. Let's find out. Okay. Let's find out. So, R equivalent is given 1 ohm, right? Okay. So, and we know R equivalent is equal to R1 plus R2. So let's find out R1 from here. R1 will be equal to 1 minus 0.3. So this is going to be 0.7 ohm. That means this one is correct. Fine. Okay. Now, what you did V1 will be equal to I into R1. Okay, that is equal to how much? I is 0.1 ampere into R1. R1 is how much? 0.7. So this is going to be 0.07. Very good. Now V2 is equal to I into R2, which is equal to 0.1 into 0.3. So this will be 0.03 volt. But is V is equal to V1 plus V2? If you add,
No, sir.
No, sir.
you are getting 0.1 volt, right? But how much is it? 3 volt,
3 volt.
right? So that means all the calculations are wrong. Either it cannot be 1 ampere or it cannot be 3 volt. So you can write down here that this question is incorrect and the correct potential difference is only 0.1 volt of current has been drawn from the battery. Got it? The battery can provide only 0.1 volt of potential difference. Understood? That's what I wanted to check whether you guys will understand this or not. This problem is really simple, but you have to understand this. V1 plus V2 should be equal to V, right? Yes or no?
Yes, sir.
Yes, sir.
Any doubt or any confusion, anyone? Anyone? No doubts? Still no doubt? Wow. Either I'm the best teacher or you are the best student. Atish will be like, second option is correct. Atish? How many of you are? Yeah, okay. Let's do resistance in parallel. Okay, I think we haven't done that. So that will be next topic, resistance in parallel connection. Okay, resistance in parallel connection. Now, how do we say whether the connection is parallel or it is series? Suppose now we have understood this, that this is R1 and R2. Now same amount of current is going, so this R1 and R2 are in series. Okay, but if we have a junction, something like this. You see there is a junction 1, junction 2. That means if you supply a potential, see potential difference between V1.1 and 2 will remain same, right? We write what? V2 minus V1, sorry, V1. So the potential difference will remain same, but suppose this is R1, R2 and R3. Now if the current drawn is I, here current going is I1, here it is going I2, here it is going I3. See, 3 different current is going. Remember this Kirchhoff's law, right? That's what we just studied now. This one. Sum of incoming current is at junction, it will just split up. Okay, all the currents. Unless it is given that current is going in the opposite direction, but still it will be a different current. The magnitude wise, it will be different. Okay. And again, see here also it is I1, I2, I3, it is going out. Now again, it will meet at meet at point 2. Again, here it will be I. Okay. So when the connection are in parallel, it will have different current in different resistance, but will have same potential difference. So what will be the potential difference here? See V2 minus V1, right? So in this V2 minus V1 is equal to V, whatever you are writing. In second resistance also it is V2 minus V1. V2 minus V1, which is equal to V. Even in third one also it is what? V2 minus V1, which is equal to V. So the potential remains constant in series parallel connection. We see this, right? Any doubt, anyone? This explanation that I'm giving is, do you have any doubt? See, in this junction, if you point out at this junction, see in all the resistance, it is the potential difference is always V2 minus V1. Okay, it's never like in that second one, it is something else, or in the first one, it is something else. but it will always be the same. Can we see this or not? It's literally right in front of our eyes, right? Anybody is having doubt understanding this, please tell me, because this is important. This will keep coming up. That's how you are going to differentiate between series connection and parallel connections. Okay, no doubt. Narayani, any doubt? Tanishka?
No doubt, sir.
Afan, anyone? Yeah,
Okay.
Narayani, you raised your
Best-
hand.
No, sir. I raised my hand to answer a question. I forgot to look.
Okay. Anyone is having doubt? Neeraj, Rakesh? Anyone?
No,
Sanjay,
sir.
you are there? No? No doubt. Oh, wow. That means I feel like I feel very good today, right? Whenever I'm in class, I feel like, okay, I'm not working hard enough. These guys are not understanding anything. But online, everyone understands everything. That's the trick, right? All the exams should be conducted online. Right? Okay. So, so we see here that all the connections will have different value of current. So I will be equal to I1 plus I2 plus I3. Now, I1 will be what? According to Ohm's law. What is I1? V upon R1. I2 will be V upon R2. I3 will be V upon R3. Yes? Is it
Yes,
or not?
sir.
Yes, sir.
Okay. So these value, if we substitute it here, what we'll get? I is equal to I1, that is V upon R1 plus V upon R2 plus V upon R3. Okay. Now let's make an equivalent circuit for this, equivalent diagram. So equivalent means we'll combine all the circuits. So R equivalent, all the resistance. Okay. And we'll just make it such that we have only one connection. So this is positive, negative. Current will go from here and so I. So from here, can we write I is equal to R equivalent? Sorry, my mistake. V upon R equivalent. See, everywhere you can write V is equal to V2 minus V1. Okay, everywhere. Here, everywhere. Here. Because here V2 is equal to V2 minus V1. Everywhere. You have to understand this thing. There is nothing called just V. Just V is electric potential and it cannot be written in values because we are bringing a test charge from infinity to some point. So we are always writing potential difference, that is V2 minus V1. Okay. So this will help you understand whether the connection is in series or in parallel. All right. Okay. So if let's say this is equation number 1 and 2. So substituting 2 in 1, what will get? V upon R equivalent is equal to V upon R1 plus V upon R2 plus V upon R3. Okay. Yes. Okay. Moving ahead. So we can take V common in both. So V we are taking common, so we can write 1 upon R equivalent. Atish, you understanding? Any problem, Atish? 1 upon R1 plus 1 upon R2.
No, sir.
1 upon R3. Okay, so can we cancel, Afan, can we cancel out these two? See, cancelling doesn't mean 0, okay, by the way. If you're bringing it to this side, this means V upon V and this will be 1. Okay, cancelling doesn't mean 0. Please don't do that. Okay, I've seen guys doing that, so please don't do it. Okay, so V will get cancelled out and what will remain? 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. That is your equivalent resistance. That's how we find in parallel connection. Ajay, tell me, in our home, what kind of connection do we have? Parallel or series?
Parallel.
Why? Why do we need parallel connection?
So, sir, if it is in series,
Huh? Tell me. Yeah, repeat. What are you saying? Say it again.
Can I tell, sir?
Yeah, of course, please.
So if it is connected in series and there is one resistor which it is not working, then the whole current will be blocked. But in the case of parallel, if even the one resistor is not working, others will continue working and the current will be passing through it.
Yes. See what happens. Then actually we haven't studied heating effect of current. That's why probably we won't be able to answer it properly. What will happen when the connection are in series? It will draw more current. Okay, and it will heat up the circuit, and one by one it will start fusing, and the amount of voltage it will require in other connection it will get lesser, right? Because see, in series connection voltage are getting consumed, right? Here you have different voltage, here you have different voltage, here you have different. The voltage will keep reducing, right? The voltage will keep on reducing. So the last connection, suppose you have a bulb, you have a fan, you have AC running, the amount of voltage they need will not be fulfilled. And that's why we need a parallel connection, because in parallel connection, the potential difference or the voltage remains same. Okay, so that's the reason. Got it? Actually, more precisely, it's because of the heating effect, but we haven't reached that far. So I think you guys can understand it. All right. So see now how let's do some of the problem and find the equivalent resistance of the circuit. Okay. So find. So this is again a question. Find equivalent resistance. Okay, I'll give you the circuit. So it's okay. Yes, how much is the equivalent resistance? Atish, R equivalent is how much? Yeah. Can anyone answer? Just tell me.
Sir,
Don't
3.
3. How?
The 3, sir.
How is this 3? See, just find out junctions. 1, 2, right? And this is separate. That means if say this is R1, this is R2, okay? And this is R3. So in R1 and R2, same potential difference is there. If this is 0.1, this is 0.2, this is 0.3. So in R1 and R2, you see same amount of voltage is going, right? Current is getting split up. So here if it is coming I, so here it is going I1 or I2 or here and here I1. Okay, again it is combining and I is going here. Right? So that means R1 and R2 are in parallel. So R equivalent for this will be 1 upon 1 plus 1 upon 1. Okay, so that is equal to 2. Sorry, my mistake. Yeah, it is 2, right? So R equivalent from here will be equal to 2. Now, 1 upon 2. No? Why nobody is correcting me? I keep on making mistake. So R equivalent is equal to 1 upon 2. Now the R equivalent of the total circuit, complete circuit. So this is the, right? So this we have got 1 by 2 ohm and this is 1 ohm. Now this is in series connection. Okay. So R equivalent here will be equal to 1 by 2 plus 1, that is 3 by 2 ohm. Anybody, any doubt? See, always draw this diagram, following diagram. Okay, do not just directly keep writing this thing. Okay, because you will make mistake, definitely. Whatsoever smart you think you are, but we do make mistake there all the time. Okay, got it? Okay, I'll give you another circuit.
Yes.
Try to find out. Can you do it? Let's see. Okay, so the network I'm giving. So this is 1 ohm. Again, this is 1 ohm. 1 ohm. 1 ohm. 1 ohm. Okay, and it's being connected to a cell. Tell me, find equivalent resistance. R equivalent, find out. It's super easy.
So we have to find R equivalent.
Yeah, of course, R equivalent. You have to.
So that will be 2 ohms.
How
Yes,
you
sir,
will
2
do it?
ohms.
2 ohms, sir.
So the next diagram, the follow-up diagram. Okay. So that means R equivalent first. These two are in series. Oh, sorry. These are in parallel. Okay.
Yes, sir.
This and this are in parallel. This
Yes, sir.
this are in parallel, and all three are in series. So I'll draw the parallel connection first. So that so this is R equivalent of parallel. This and again this. Okay, Atish, you understood or not? So R equivalent of this circuit will be how much?
1 by 2.
1 by 2. R equivalent of this circuit will be how much?
1 by 2.
1 by 2.
And this already is 1, right? So R equivalent of this complete circuit will be 1 by 2 plus 1 plus 1 by 2. How much is this?
2.
2 what? Elephant?
2 ohms.
Ohms, sir.
2 ohm. I thought Afan, Akshay Kumar is going to. Okay, let's not say that. Otherwise, he'll file a complaint against me. That this
Yes,
guy. You will do that, no?
Very
Afan,
not, sir.
you will do that. Okay, fine. I'm not scared of you, Afan, because I'm very far away. So you can't. Acha, listen. So let's find out for this circuit. Okay. This is better. So let's say this again. All are 1 ohm. And I'm drawing current from. Find out R equivalent. Always draw the follow-up diagram. I don't know if it is there in the book or not, but draw the follow-up diagram. You will understand why I'm saying. You will never make mistake. You will have a very clear idea which are in series and which are in parallel. Atish, which connection are in parallel? Which are parallel connections?
Sir,
Okay, let me write R1.
sir. Okay.
Can you see this yellow color?
Sir, R1 and R5 is parallel.
R1 and R5.
Yes, sir.
Achha, which all are in series?
Sir,
Yeah, who's this?
sir, I want to tell the answer. It's 1 by 2 ohms.
Okay, so that means you got the answer. No? Okay, fine. Let's wait and see. I don't know what the answer is. I don't know. Let everyone get the answer, then we'll solve it. See, R4 and R5 are in series. R1 and R2 are in series. Why? Because current is coming here. Now this is a junction. So let's say here it is going I1, I2, I3, right? Now same current is going here, I3. right? Here same current is going I1. So if same current is going, that means it's a series connection. So if you draw the equivalent diagram for this, you can draw like that. Even you can, if you want to, you can arrange this diagram like this. So this is your R2, R1, this is R3, R5, R4, and we are giving connection here. Okay. 1, 2. Now equivalent diagram, let's make. Now these three are in parallel. How? Now this is R1 plus R2, R2 plus R1. This one is R3 and this one is R5 plus R4. Okay. So this is equal to 2, 1, 2. Okay. Now R1 upon R equivalent will be equal to 1 upon 2 plus, 1 upon 2 plus 1 upon 1 plus 1 upon 2. Right? So this is going to be how much? This will add up to 2. So R equivalent will be equal to 1 upon 2. Ohm. Okay, that I need. Not elephant. Ohm. Huh?
Yes.
You will say ohm when you are saying the answer. Everyone got this?
Sir.
Yes, sir.
Anyone having doubt? Anyone? Atish, any doubt? Or you understood everything?
Yes, sir. No doubt.
No doubt. Oh, cool. Nice. Afan?
Yes,
Afan?
sir.
Okay, no doubt now?
Yes, sir. Clear.
Acha, Afan, you will tell the answer of this question, next question. Okay? Afan? Okay,
Yes,
calculate. Okay, this is the easy one. Calculate number of electrons constituting 1 coulomb in 1 coulomb of charge. Afan, tell me the answer.
What's your question, sir?
This is a question. Calculate number of electrons in 1
Okay, sir.
of charge. 1 coulomb.
1.6 into 10 to the power minus 19.
Do it, tell me.
Sir, 1.6 into 10 to the power minus 19.
1 coulomb upon 1.6 into 10 to the power
Minus 19.
minus 19 what? Coulomb?
Oh, yeah, coulomb, yeah.
This will be 6.25 into 10 to the power
10 to the power
18
18.
electrons. Okay. Atish, any problem? Any doubt? Sorry. Okay. I think you guys have understood this properly, but let's do another question. So I will give you a circuit. So let's say this is 2 ohm, 3 ohm, 5 ohm, 1 ohm. Now this is point, let's say A and B. Okay. And I'm giving a potential difference VA minus VB is equal to 5 volt. Okay. Find I. Find current in all resistors. Okay. Let's see who can do this. See, if you guys can solve these type of problems, that means your concept is clear. Okay. Otherwise, you are still struggling with your concept. You know that You may think that you know the concept, but believe me. Let's solve it. Do it. So see, this will be the last problem that we'll do today. And tomorrow we'll study the heating effect of current and we'll end the chapter. Okay. And we'll solve the problems based on that. And hopefully tomorrow we'll wind up this chapter. Yes, how many of you got the answer? What you will do? How you will proceed? Anyone? See, first, current, let's say current is I is going in this conductor, okay? That means current I will be going out. Okay. Now let's say the current gets split up here. I1, I2. That means these two connections are in parallel. Okay? Yes or no? Everybody left or what?
Yes, sir.
Yeah, tell me, any doubt? So we need to find I1 and I2. That's our goal. Okay. Yeah, go on. Don't expect me to solve it. I'm just giving you a hint. Find R equivalent first. Equivalent circuit first. Find out. If you can find out R equivalent, so what you can get current from here? I will be equal to V upon R equivalent. So you'll get I. Okay. Is it too hard? Narayani, what happened? Tanishka.
Just sir, I'm calculating R equivalent.
Okay. Tanishka, what happened?
I'm getting R equivalent as 39 by 8.
I don't know. How would I know?
That's what I got. So I is equal to 40 by 39.
Jishnu, how much you are getting?
I also got 40 by 39.
40 by 39, sir.
Okay, let's do it. So let's name this point C, this point D. Okay, so that it will be clear. This is A and These two are in. Okay, so this point is C, this is D, and this is A, and this is B. Okay, that means there is a connection here. All right. Now, this is 2. This is 1 upon 3, 1 upon 3 plus 1 upon 5. How much this will be?
15 by
8 by 15.
8 by 15.
8 by 15. So this is 1 upon R equivalent. R equivalent will be equal to
15 by 8.
15 by
15 by 8 ohm. And here this is 1 ohm, right? So R equivalent of the circuit will be what?
39 by 8.
39 by 8.
Let's write here R equivalent is equal to 2 plus 1, 3. So 2 plus 15 by 8 plus 1. How much will be this?
39 by 8.
39 by 8.
39 by 8 ohm. So this is R equivalent you got. Now from here you can find I. Now I is going here. Throughout I is traveling only. I everywhere, right? In this circuit. So I will be equal to what? Because V is given, right? V is given to you 5 ohm. So I will be equal to 5 upon 39 upon 8. So that will be 40 upon 39 ampere. Fine?
Sir.
Yes?
Yes, sir.
So you got I. How about I1 and I2? How you will get I1 and I2?
I1 is 2.5.
Okay, see, here I1 plus I2 will be equal to I. Fine?
Yes, sir.
Yes or no?
Yes, sir.
Okay. Now, how you will find I1 and I2? Okay, you know I1 plus I2 will be equal to 40 by 39. But how you will find it? What else we can do? See, there the voltage here will be VAC. That means VC minus VA or VA minus VC. Here, the potential will be VC minus VB. These two are in parallel, right? So in this resistance, this is the potential. Here, the potential will be VD minus VB, right? This is VA minus VC. So the potential in all these three resistance will be different, right? Potential difference of all the three resistance will be different, isn't it? So use this concept and find out the value of I1 and I2. Okay, so that is your homework. Tomorrow I want that. Just struggle a little bit. If you won't struggle, you won't get anything. So your homework is to find I1 and I2. You can take help of your book. Use your book. Okay, and find out. This is your homework. I have told you the concept in because see here potential difference is VA minus VC. Here the potential difference is VC minus VD. Here the potential difference is VD minus VD. You have three potential difference, three resistance. You can get current from there. If you can't do now, I don't know how you will do it. So this will be your homework, okay? Yes or no?
Sir, can we go a little bit up?
What?
Can
Who is this? Afan. Is that you?
No, sir.
Okay, so who was that?
Sai Vignesh.
Sir, can you hear me?
What do you want?
Can you go a little bit up in that side?
Acha, that's what you're saying. Nitya has not been saying anything in class. Why is that? Because you did?
I did.
You just said yes, sir, no, sir. You want to go to military school or what?
No, I don't want to go to military school.
Okay, cool. So that will be your homework. All right, and please do it. And any other explanation or any concept? explanation that you want, then you can ask me right now. And if you haven't understood anything in class today, mostly we revised because you guys had revised a lot, obviously. So we did that. All right. So tomorrow you will do this homework, right? Yes or no? Atish, where is your friend Sanjay? Not here. Okay, thank you. Thank you so much for joining this class. Thank you. Tata, bye-bye.
Thank you, sir.
Thank you, sir. Bye, sir.
Thank you, sir.
Any doubt? Anyone?
No, sir.
No
No,
doubt.
sir.
All are intelligent guys. Bye.
Bye,
Bye,
sir.
sir.
Bye, sir.